Introduction. Great. Good afternoon, everybody, and welcome to the GALCIT Young Investigator Lecture to be given by Dr. Bhavini Singh. It's a great pleasure to have Bhavini come speak to us. The Young Investigator Lecture Series is hosted by the Division of Engineering and Applied Science and each department. It's an opportunity for us to get to know exciting young researchers, to have some conversations with them, and to hear about their current and recent research. So Bhavini, and she told me this morning that as of last week, when she successfully defended her thesis, she is Dr. Bhavini Singh. So congratulations. Bhavini has been doing her work. She did actually her bachelor's, master's, and PhD in the School of Aeronautics and Astronautics at Purdue. She's related. So her PhD advisor was the PhD student of Professor Joe Shepard. So she's an academic grand offspring, although Joe did tell me not to call him grandpa. But since he's in the waiting room, he's in the participant side, I can get away with saying that. It's very nice to have that connection. Bhavini's going to talk about her doctoral research, which which focused on characterizing the flow field induced by a single plasma discharge. And she's going to talk about the title here. So I will just hand over to you, and thank you again for participating.
Thank you very much for the introduction, Professor McKeon. And thank you everyone for being here. I'll go ahead and get started. And so what I will be talking about today is the shock-generated vortex rings that are driving entrainment as well as cooling in the flow field that is being induced by a spark discharge. And so what you're seeing here on the left-hand videos and images are the shadowgraph images of the spark-induced flow that's the subject of this work. And so we took these, we captured these shadowgraph images at 700,000 frames per second. And the reason we needed to go at this high frame rate was so that we could capture that shock wave that is induced at the early time steps, as well as the evolution of the hot gas kernel that's occurring over longer time scales. And so what we see here is we actuate a spark between a pair of electrodes, and the gap between these two electrodes is 5 millimeters long. And what this results in is a region of hot gas in the center of the gap, as well as a shock wave that's produced. And so what we can see in this smaller video and this large video when it replays is that the shock wave that's induced propagates radially outwards, leaving our field of view really fast out of the gap that it was formed in. And so once the shock wave moves out, we have that region of hot gas that expands and cools in time. And so what we can see from this flow field is that it's occurring over multiple time scales, and this length scale that it's associated with, that electrode gap distance, is also fairly small. And so what we wanted to study and to understand here is the cooling process of this heated region of the gas, as well as the velocity field that's induced here and the coupling that may exist between the velocity field that's induced and the cooling of the hot gas region. And so we also wanted to understand how this shock wave that's produced at the very early times contributes to the flow field that evolves at the later time steps. And so I'll go through in these next few slides our efforts in understanding this flow field and showing that this shock wave that's generated at the early times contributes to vortex rings that are generated in this flow field, which in turn drive entrainment into the gap and cool this region of hot gas that we're seeing in the spark discharges. And so the spark discharges are just one subset of plasma discharges, and plasmas can affect the flow in a few ways. They can alter the chemistry of the flow fields. They can also provide localized heating via the thermal mechanism, and they can also induce a flow either in the form of ionic wind or via the thermal mechanism. And so we are specifically interested in nanosecond sparks or nanosecond spark plasma discharges, and these induce a flow field via that thermal mechanism. And so we generate the nanosecond spark discharges by applying a voltage difference across two electrodes. And this results in the breakdown of the gas between the electrodes and is accompanied by an ultra-fast two-step heating mechanism that results in the localized heating as well as production of shock waves in the flow. And so we are motivated to study these plasma discharges because of that induced flow field that they produce. It provides us with an opportunity for flow control as well as combustion control. And these spark discharges specifically are advantageous because we can turn them on and off depending on when we need them. And they're also advantageous because of their low duty cycle, large bandwidth, as well as lightweight. So researchers have shown different types of plasma discharges that have shown the capability of reattaching separated flow. Behind here, where this work was done on a cylinder. And spark discharges specifically have been shown to be very promising for combustion enhancement, where they can promote lean combustion, which would in turn reduce pollutants in the environment. However, a lot of this work on the applications of the spark discharges has been based on trial and error. And before we can design scalable high frequency actuators, it's necessary for us to first understand the flow field that they're inducing and to characterize that induced flow field. And so there has been some work in characterizing the induced flow. However, a lot of this work has been limited to qualitative studies of the flow field. There have been some quantitative studies using CFD, but a lot of these have been limited to the very early time steps of the flow field when we have the shock wave. And so what these studies have shown is that there is a region of hot gas as well as that shock wave that's produced. And so quantitative experiments are lacking because, as we saw in that first slide, in order for us to be able to properly resolve this flow field, we need high spatial as well as high temporal resolution measurements. And these are typically difficult to perform. And so we performed some, in our early work, we performed some quantitative velocity measurements of the flow field that's induced using particle image velocimetry, and we were able to see that there was some entrainment into the gap as well as a pair of vortex rings that are induced, but the spatial resolution as well as the temporal resolution of these experiments still needed some improvement. And so what we do know about these flow field, about these spark discharges and the flow field that they induce is that a shockwave is generated at those early time steps, and it departs the field of view within about 20 microseconds, in a few microseconds, and it leaves behind a region of hot gas as well as a pair of vortex rings, and there's also entrainment into the gap. And we also saw that the hot gas kernel cools in time. And so the next few slides go through a brief background on each of these stages on work that is existing before we started working on this problem. And so the early stages of the flow, there have been some CFD studies into these early stages, and these have shown that the shockwave that's formed is curved, and the shape of the shock in the center of the gap takes on a cylindrical shape, while near the electrodes, it takes on a more spherical shape. CFD studies have also shown that at the early time steps, the shockwave resembles a blast wave, but it very quickly decays into an acoustic wave at those later time steps. And so we also saw that a pair of vortex rings are generated, and there has been some work that has looked into where the vorticity is generated in these types of sparks, and researchers have shown using computations that it is primarily baroclinicity or baroclinic torque that's responsible for generating vorticity in these types of discharges. And more specifically, they found that the baroclinicity can generate vorticity via two main sources. We could have a vorticity jump across the shock because of its non-uniform strength. And we could also have vorticity generated because of the interaction of pressure gradients behind the shock with the low density region from the heated gas. And so in laser sparks, this second mechanism has been shown to be the more dominant source of vorticity production. But I should mention that in laser sparks, the energy that's deposited in the gap is 10, 20, sometimes higher than what we see in our nanosecond spark discharges. And so the relative contribution of each of these sources of vorticity generation is still not well known in nanosecond sparks. and more specifically, the experimental investigation of the mechanisms that are driving this vorticity generation is still lacking. And so we also saw that once the shockwave departs, we have this region of hot gas that's also left behind. And a lot of the work that has looked at these later stages of the flow field has primarily been qualitative. And so researchers have shown from their studies that as the hot gas kernel cools, it takes on this torus shape. And they've hypothesized that there's a velocity field that's induced, and that induced velocity field, there's a coupling between that induced velocity field and the cooling of the hot gas kernel. And so, as I mentioned, our earlier work did show that there is an induced velocity field that comprises primarily of this entrainment into the gap as well as a pair of vortex rings. But the exact coupling that exists between the induced velocity field and the cooling of the hot gas kernel wasn't very clear. And then finally, researchers showed using qualitative studies that depending on how much energy was deposited in that gap, the region of hot gas expanded to different extents, so expanding more for the higher energy values that were deposited in the gap. And so another thing we wanted to understand was how varying the energy deposited in the gap affected the hydrodynamics of the induced flow field. And so this brought us to our main research objective, which was to quantify and to understand that flow field that's induced due to just one single spark discharge. And we produced that spark discharge at standard atmospheric pressure and temperature. And so in order to further study this aim, we divided our work into three main research objectives, which was to study the cooling of the hot gas kernel and to determine to what extent that cooling was convective. We also wanted to determine the role of the induced vortex rings in entrainment as well as cooling, and to evaluate the effect of energy on that cooling process. And then finally, we wanted to estimate the role of the induced shockwave in generating those vortex rings. And so if we start off with the first research objective, which is to look at the cooling of the hot gas kernel, we are hypothesizing here that the cooling of the hot gas kernel is driven by the flow entrainment. And so in order to study that cooling, we performed four main tasks. We measured the velocity field that was induced by these discharges using particle image velocimetry, or PIV, and we measured the density field that was induced using background-oriented Schlieren, or BOS. We also developed a cooling model using a control volume analysis of the energy equation so that we could relate entrainment to the cooling of the hot gas kernel. And then finally, we developed the cooling ratio parameter here that we used to evaluate the total cooling effect that was experienced by the hot gas kernel. And so to collect our quantitative velocity data, we performed stereoscopic PIV measurements. And for the density measurements, we performed background-oriented Schlieren measurements. And these were separate experimental campaigns. And we had 25 tests for each of these. Here on the left, I'm showing our PIV setup, as well as a sample video of the particle images we recorded. And so for the PIV, what we did is we directed a thin laser sheet into our test section. And that test section is what contained our electrodes. Those electrodes were made of tungsten, seriated tungsten, and they were hooked up to our high voltage pulsar that generated the spark. We then viewed the flow field that was induced using a pair of cameras that were in a stereoscopic arrangement. And the angle between these two cameras was 40 degrees, and they were recording at 10 kilohertz between image pairs. And so the magnification here was 100 pixels per millimeter, and we seeded this test section using aluminum oxide particles that had an average diameter of 0.3 microns and a Stokes number of 0.002 that allowed them to follow that flow field accurately. We then cross-correlated the image pairs to yield our displacement vectors. For the background-oriented Schlieren, we illuminated our dot pattern using a xenon arc lamp, and here our dot target was a sandblasted aluminum piece. We then viewed this dot target through our density gradient that was induced by the spark using a single head-on camera. And so this camera was recording at 20 kilohertz, and we had a magnification of about 80 pixels per millimeter. And so the distortion on the dot pattern we estimated using cross-correlation, similar to PIV, where we cross-correlated a reference image that was taken in the absence of any density gradients with an image of the dot pattern in the presence of the flow field that's induced. And so this allowed us to calculate our displacement values, which we then used to estimate our projected density gradient field. We then solved a Poisson equation for our projected density field, and we used Abel inversion to calculate our actual density field. And so if we start off by looking at the density field that was induced, so the test case that I'm showing here, the energy that was deposited in the gap was about 5.8 millijoules. And all the results that I will show in this work have been non-dimensionalized. And they've been non-dimensionalized using the induced velocity and the density behind the shock, as well as that gap length. And so we non-dimensionalized these using relations that were developed by Jones et al. And so once the video plays back again, we'll see that the hot gas region that's heated by the spark, it starts off in a sort of cylindrical shape initially. And once it cools, it takes on this torus shape, similar to what we saw in the qualitative studies in the beginning. And so what we wanted to do was to identify what our hot gas kernel was, and we identified this as regions with a density value less than 95% of the ambient, and we're outlining that kernel in red here. And so what we then did is we calculated the mean density of all the points within this kernel, and we plotted a time history of that mean kernel density. And what we can see here is that the hot gas kernel is cooling in time, and we can see that from the increase in density with time. But more interestingly, we're seeing that that cooling is occurring at two distinct rates. We have this first cooling regime where the cooling rates are higher and is our fast cooling regime. And we have this second cooling regime where the cooling rates are slower and is our slow cooling regime. And so we performed the same analysis of identifying our kernel and identifying the two cooling regimes, and then fitting a straight line and using the slope of those lines to calculate the cooling rate in each of those cooling regimes for all of our tests. And so here I'm showing the cooling rate values in the fast cooling regime and the slow cooling regime for all of our tests. And what we can see is that the cooling in that fast cooling regime is 2 times or more higher than the cooling rates in our slow cooling regime. And I should point out that this fast cooling regime is occurring within 1 to 1.5 milliseconds. And in the range of energies that we investigated, we didn't see a clear effect of energy. And so this work focuses on studying the cooling in this fast cooling regime. And so from the velocity field from our PIV, we calculated the vorticity field, and we used the vorticity to identify our coherent structures that comprise the vortex rings. And we identified these using the lambda CI method, such that all points that had a swirl strength greater than 10% of the max value were considered coherent. And we also see then from these results that we have a pair of vortex rings that are induced near the electrode tips initially, and we also have entrainment into that gap. And so we use these results to also calculate our ring properties, such as the core radius, the ring separation distance, and the ring circulation. And we also identified the weighted centroids of the cores of those vortex rings. We then use that information to look at the vortex ring trajectory and the ring radius and circulation time histories. And what we see from the vortex ring trajectories is that the vortex rings move towards each other, they collide, and then they move outward and expand. And so we see that expansion also from the increase in vortex ring radius with time. For the circulation, we saw that it increases and peaks and then continues to decrease post-collision. And so we used the weighted centroids to identify our control volume for the control volume analysis of the energy equation, which follows next. And so we have now at this point our velocity measurements and we have our density measurements, and we want to relate the entrainment into the gap to cooling of the hot gas kernel. And for that, we use the energy equation where we are assuming a low Mach number flow, as the shockwave has long departed our field of view at this point. We're assuming that the flow is inviscid. We're neglecting body forces and we're neglecting heat transfer due to conduction and radiation. And so this allowed us to simplify our energy equation and write it in terms of total enthalpy. And we can rewrite this equation and evaluate the volume integrals. And if we further assume that the volume flow rate into our control volume is equal to the volume flow rate out of our control volume, and that cold gas that's coming into our control volume is mixing perfectly with the hot gas before exiting the control volume, we can further simplify the energy equation into this boxed equation, which is our cooling rate equation. And what we can see from this is that the left-hand side of our cooling rate, we can evaluate purely using density measurements that we measured from BOSS. And the right-hand side is our cooling rate equation that we can calculate from the entrainment, which we can calculate from velocity measurements from our PIV. And so we went further and developed a more meaningful parameter from the cooling rate equation to evaluate the cooling of the hot gas kernel, and that's the cooling ratio term. And what the left-hand side of this cooling ratio term represents is the total cooling effect that the hot gas kernel experiences in that fast cooling regime. And the right-hand side represents the total amount of cold gas entrained as a fraction of the control volume, once again in that fast cooling regime. And so the closer this cooling ratio value is to 1, the more complete the cooling process. So when we have a cooling ratio value of 1, it means that the hot gas kernel has cooled to ambient. And so if we look now at the plot of our cooling ratio values calculated from our density, so our density-based cooling ratio values from BOSS, and we compare that to our entrainment-based cooling ratio values calculated from PIV, we see that the entrainment-based cooling ratio values are statistically equivalent to the density-based cooling ratio values. And what this shows us is that it's the entrainment that's largely responsible for the cooling in that fast cooling regime. If we further look at the values of this cooling ratio, we see that it ranges from about 0.3 to 0.5 or slightly higher. And this tells us that about 30 to 50% of that hot gas kernel is cooling in that fast cooling regime, and that cooling is occurring within 1 to 1.5 milliseconds. And so these findings are significant if you want to determine the frequency at which you should be pulsing your actuators or the actuator spacing. And we do see variability in the results, and this can arise from experimental uncertainties, but in this case, it can arise more so from the fact that our density measurements and our velocity measurements were non-simultaneous. And so each spark realization is different because of that stochastic nature of the generation of the sparks, and so this leads to any further mismatch and scatter in the data. And this leads into our second research objective, which was to determine what role those induced vortex rings play in entraining the cold ambient gas and cooling the hot gas kernel. And we also wanted to evaluate the effect of energy on that cooling process. And so here we're hypothesizing that the entrainment as well as the cooling of the hot gas kernel is driven in that fast cooling regime is driven by the induced pair of vortex rings. And so in order to determine the role of the induced vortex rings, we performed 3 main tasks. We developed a vortex ring model to calculate the entrainment as well as the cooling due to the rings. And we designed this time simultaneous measurements of density and velocity using simultaneous PIV and BOSS experiments. We also evaluated the effect of energy on the induced flow field. And so we developed this cooling ratio term in the previous research objective. And here we related the cooling of the hot gas kernel to the entrainment into our gap per unit volume. And so in that case, the entrainment was evaluated directly from the velocity field that we measured using PIV. And so here we start off by defining our control volume, similar to what we did in the previous research objective. It's located between the weighted centroids of our vortex rings, and it takes on this cylindrical shape. And so as the rings move towards each other, the shape of this control volume is also changing. And so in ring fixed coordinates, the entrainment into the control volume is given by this equation, where UZ is our axial velocity and capital UZ is the ring velocity. And so if we write our radial and axial velocities in terms of the entrainment function, where the entrainment function is equivalent to the stream function in incompressible flows, this allows us to write the entrainment into our control volume in terms of the entrainment function and our ring velocity. And so what this tells us is that the entrainment into our control volume is the difference in the entrainment function at the centroid of the ring and the entrainment function at the axis of symmetry plus this added term due to the motion of the ring. And so what we want to do is to calculate this entrainment function and ring velocity using vortex ring models to calculate our entrainment. And we'll do that on the next slide. And I just wanted to point out a few key terms here. So A here is the core radius of the vortex rings, R is the ring radius of the ring, and gamma is the circulation of the vortex ring. And so F and UZ are the entrainment function and the ring velocity. And so to calculate the total entrainment into this control volume, we'd have to account for the entrainment due to both the top and the bottom vortex ring. And so to calculate the entrainment function, we can use existing vortex ring models. Because we are assuming that our flow is a low Mach number flow, our flow is acoustically incompressible. And therefore, any changes that we are seeing in our density are due to changes in temperature. And we can therefore use vortex ring models that are developed for incompressible flow to estimate the entrainment function as well as the ring velocity. And so what we need to do is calculate the entrainment function inside the core, outside the core, as well as the ring velocity. So the entrainment function outside the core was developed by Lamb, and we can use the filament model for that, and it's valid for distances far away from the ring centroid. It assumes an infinitesimally thin ring as well as incompressible and inviscid flow, and it's given by this equation, and this allows us to calculate the entrainment function at the axis of symmetry. To calculate the entrainment function inside the vortex ring core, we use the derivation by Safman, where if you take the limit of the filament model as R tends to the ring radius, and further, if you assume that the distribution of vorticity inside the core is uniform, we get this equation, and this allows us to calculate the entrainment function at the centroid of the ring. And so this also assumes incompressible inviscid flow, and it assumes that the core radius is much smaller than the ring radius. To calculate the ring velocity, we calculated it as the self-induced ring velocity. And the reason we could do this is we found that the influence of the second ring in that fast cooling regime is negligible. And so in this way, we can calculate the entrainment into our control volume in the fast cooling regime purely using the vortex ring model. And so we captured the induced velocity field and the density field using simultaneous PIV and BOSS experiments. And we did this so that we could test the vortex ring models on our Spark data. And so the PIV setup and the BOSS setup from the previous research objective were essentially combined here into the simultaneous measurements. And so we see the center camera, which is our head-on camera, being our BOSS camera for the density measurements, and the two outer cameras in being our PIV cameras in a stereoscopic arrangement, having an angle of 50 degrees. And so the experimental parameters were very similar to those in our previous research objective. And in this case, we varied the energy deposited in the gap in a controlled manner by adding resistances in series with the gap, allowing us to vary the energy from about 2.2 millijoules to 5.1 millijoules deposited in that gap. And so once the velocity data and the density data were collected, we can flip and average the 2D grid along our electrode axis. And this allows us to create a spatially averaged axisymmetric field. And so in this field, we can calculate the density as well as the vorticity. And from the vorticity, we can identify once again our coherent structures, the cores of the vortex rings, as well as identify the weighted centroids of those cores. And using this, we can then define our control volume, which we then apply to our density field. And we calculate the mean density within this defined control volume. And once again, we see that our cooling is occurring at two distinct regimes. And we're interested primarily in the cooling in this fast cooling regime. So we determine the start and end time of the convective cooling regime from this. We then calculate the experimental entrainment function from the velocity field that we measured using PIV, using optimization via least squares, and we do this over the duration of that fast cooling regime. This allows us to then calculate the total instantaneous entrainment from our experiment. And we calculate the ring properties from our experiments as well. We calculate the ring circulation, ring radius, and core radius. And we use this as inputs into our vortex ring models, and therefore calculate the total entrainment into our gap from the vortex ring models. And so here we see the density field as well as the vorticity field with the entrainment function superimposed on the vorticity field. And the videos are showing the evolution of the hot gas as well as the rings for the highest energy case as well as the lowest energy case in our experiments. And on the right, I'm showing the hot gas kernel superimposed on our vorticity field. And so what we see is that the hot gas kernel starts off as a cylindrical shape with the vortex rings located near the tips of the electrodes. And as the vortex rings move towards each other, this hot gas region is also compressing axially. When the rings then collide and expand outward, we also see the same motion in the hot gas kernel where it expands outward as it is cooling. And so at the later time steps, we see that the vortex rings are located almost entirely within that hot gas kernel. And so what we are seeing here is there's this strong coupling between the vortex ring dynamics and the hot gas kernel cooling and expansion. And for the higher energy values, we see that we have more heating signified by the lower density values, and we have stronger vortex rings as well as more expansion of that hot gas kernel as well as the vortex rings. And so with the data from our vortex ring models, as well as our experiment, we can plot the entrainment that we calculated from our experiment via the least squares optimization, and also plot the entrainment that we calculated from our model. We can also plot the cooling ratio from our density, from the density alone, and we can compare the cooling ratio from our entrainment-based calculations to that. And so here, the entrainment-based calculations are both one from the vortex ring model and the other from the experiment. And so if we start off by looking at the entrainment, we see that the model-based entrainment calculations agree with the experimental entrainment calculations, and they fall within the experimental uncertainties and within our confidence intervals. And this tells us that the entrainment we calculated using our vortex ring models is statistically equivalent to the entrainment we have in our experiment. And this shows us that the vortex rings drive the entrainment into our electrode gap. If we then look at the cooling ratio results, we see that the entrainment-based calculations of the cooling ratio underpredict the cooling ratio calculated from our density-based measurements by about 14%. And so the mismatch may arise due to the assumption that we made that our vortex rings are axisymmetric, which goes into our entrainment calculations. It could be that our vortex rings are more three-dimensional than we expect, which would affect the entrainment-based calculations. Overall, though, we see that there is an agreement between the entrainment-based cooling ratio as well as the density-based cooling ratio. And this once again is showing us that it is the entrainment that's largely driving the cooling in that fast cooling regime. But further, the fact that the entrainment-based cooling ratio calculated from the vortex ring models agrees well with the density-based cooling ratio tells us that it's the vortex rings that are driving the entrainment in that fast cooling regime and leading to the cooling of that hot gas kernel. If we continue to look at the cooling ratio plot, the lower energy values are shaded lighter than the higher energy values, and we see that more cooling is occurring at the higher energy values. And actually, we're seeing that more than 50% of that hot gas kernel is cooling for the higher energy values in that fast cooling regime. And so we can see how what an important role these vortex rings are playing in setting up the flow field at these later times and cooling the hot gas kernel. And so one other thing we wanted to learn was what role that shock wave that's generated at the early times, what role it plays in generating the vortex ring vorticity. And so here we're hypothesizing that the shock wave contributes to the vortex ring vorticity. And in order to estimate the vorticity jump across the shock, we designed Schlieren experiments to capture that shock wave, and we used a model to estimate that vorticity that's generated by the shock. And so, as I mentioned earlier, researchers had shown that in these types of spark discharges, it is the baroclinic torque that's primarily responsible for vorticity generation, and that vorticity generation due to baroclinicity can arise from two main sources. We can have a vorticity jump across the shock due to its non-uniform strength, or we could also have vorticity generated from the interaction of pressure gradients behind the shock with that low density region. And so here we focus on this first mechanism of vorticity generation. And so the vorticity jump across an unsteady axisymmetric curved shock in quiescent flow is given by this equation developed by Hayes, where he showed that the vorticity jump across the shock is dependent mainly on the magnitude of the tangential component of the shock velocity. So here US is the normal shock velocity, and this is the coordinate system fixed in the shock. And so we can rewrite the vorticity jump across the shock in terms of the horizontal component of the shock velocity, the shock angle, as well as the shock curvature. And this last term is our density ratio term. And so to use the model and to capture the shock wave, we used Schlieren experiments, and we recorded these at 700 kilohertz, and the resolution here was 64 by 128 pixels, giving us a field of view of 5 by 10 millimeters. And so to estimate the vorticity from the shock, we developed a correlation-based data processing procedure to estimate the shock parameters from our Schlieren images. And so first, to detect our shock outline, we pre-processed our Schlieren images by subtracting the background. We then flipped and averaged the shock profile along the center line, and we performed a line-by-line spatial cross-correlation to detect our shock outline or our shock profile. From this, then, we were able to obtain our shock angle as well as our shock curvature. To calculate our normal shock velocity, we windowed the pre-processed images, and we cross-correlated subsequent images taken at 3.5 microseconds and 4.9 microseconds after the spark. And we did this so that we could calculate the shock displacement, which we then used to calculate the shock Mach number and in turn calculate the density ratio. We then combined our shock velocity calculations with the shock angle calculations to calculate our tangential shock velocity, and we combined these terms to calculate our vorticity, the spatial distribution of our vorticity, and we did this for all of our time steps. And so here I'm showing a Schlieren video of the shock wave as it's moving out of the gap, and this first figure on the left shows the shock profile from that first time step for all of our tests. I'm also showing the shock curvature, the tangential shock velocity, the density ratio, as well as our vorticity, and these are all normalized by their peak values. And so what we see from the curvature is that near the center of the gap, we have negligible curvature close to zero, and the curvature increases as we head towards the electrode tips. From the density ratio, we see a nearly constant density ratio in the center of the gap, and it decreases slightly as we move towards the electrode tips, telling us that the shock strength is also decreasing slightly as we move towards those electrode tips. For the vorticity, we see that there's negligible vorticity generated in the center of that gap, and the vorticity peaks as we move towards the electrode tips. And so if we look at the location at which that peak vorticity is occurring and the location at which the peak curvature is occurring, on average, we see that that peak vorticity is occurring at the point of peak curvature. And so if we plot the value of curvature, tangential shock velocity, and density ratio at the that go into calculating that peak vorticity, and we plot these as a function of the pressure jump across the shock, which is a function of the energy deposited in the gap, we see that the curvature and density ratio increase with an increase in energy, and we have negligible effect on that tangential shock velocity. And so if we compare the shock generated vorticity to the vortex ring vorticity, which here we calculated from the PIV measurements in our previous research objective, we see that overall the shock generated vorticity is statistically equivalent to the vortex ring vorticity. And this tells us that the shock wave contributes to the vortex ring vorticity. We do, however, see considerable scatter and negligible dependence on energy in these measurements. And the work is limited because the measurements of the shock and the velocity field were non-simultaneous. And so that stochastic nature of generating the sparks means that each spark realization will be different. And so that further leads to scatter and any mismatch. We also see that the shock-generated vorticity has high uncertainty values. And finally, the other thing is that the shock images that we captured here were taken about 3 or 4 microseconds after the spark, and we're comparing them to the vortex ring vorticity that's taken about 30 microseconds after the spark. And we know that we can have vorticity altered post-generation, and this can further lead to any mismatch in the scatter that we're seeing. And so this leads us into the summary of this work. And so we had two main, we started off with a couple of research objectives, which was to look at the cooling of the hot gas kernel, as well as determine the role of those induced vortex rings in the entrainment and cooling. And we investigated nanosecond sparks using quantitative measurements of particle image velocimetry and background-oriented Schlieren that allowed us to measure the induced velocity field and the density field. And what we saw is that there's a hot gas kernel that's induced as well as a pair of vortex rings, and that the dynamics of the vortex rings and the cooling of that hot gas kernel are highly coupled. We saw that that cooling of that hot gas kernel occurs at two distinct regimes, with that fast cooling regime having higher rates of cooling and occurring within 1 to 1.5 milliseconds. We saw that the cooling in that fast cooling regime is driven by the entrainment, and further that it's the vortex rings that are leading to that entrainment, and that we have more cooling for higher energy values. In fact, more than 50% of the hot gas kernel is cooling in that fast cooling regime within 1 to 1.5 milliseconds for the higher energy values. And so what we found is that spark discharges are inducing a vortex ring driven mixing, and therefore controlling the strength of these vortex rings can control the actuation frequency of future plasma designs, as well as the actuator spacing for these designs. Our third research objective was to look at the role that that induced shockwave at early times plays in generating the vortex ring vorticity. And what we saw is that a shock of non-uniform strength is generated that leads the shockwave to be curved, and that we have vorticity, peak vorticity being generated at the location of peak curvature. We saw that overall, the shock-generated vorticity is statistically equivalent to the vortex ring vorticity, which shows us that the shockwave does contribute to the vortex ring vorticity, with still more work left in this field. And so this leads us to some suggestions for future work. And so the work that has been done here can be extended to actuate the spark discharge in the presence of external flow. And we can use the cooling ratio that's developed in this work to investigate the cooling in those types of flows. We can also extend the work on vorticity generation to assess the relative contribution of the two baroclinic vorticity generation mechanisms. And in order to obtain high spatial and temporal resolution of the velocity and density field, the studies could start off with CFD studies that can investigate the flow from the moment the shock is generated a little less than 1 microsecond after the spark to the moment the vortex rings are fully formed about 50 microseconds after the spark. The work can also be extended to multiple actuators that are spaced 1 ring diameter apart, as well as multiple pulses that can be actuated within that fast cooling regime. And we can not only assess the cooling in these discharges, but also assess the interaction of the vortex rings and the 3D nature of the flow. And so this work has also been extended by Rajendran et al. To surface discharges where the spark is embedded on a surface. And the vortex ring models were used to predict the length as well as the time scales of the flow induced. And from there, similarly, future work can investigate the effect of multiple surface discharge actuators as well as multiple pulses and perform 3D measurements of the induced flow. And so I'd like to end with a few acknowledgements. I'd really like to thank Dr. Bain, who was my PhD advisor and who led and guided the research projects that I discussed here, as well as Professor Vlahos for his guidance on the measurement techniques employed here, and to Dr. Rajendran for his collaboration on the projects, as well as his insights on the BOSS measurement techniques applied to plasma flows. Also, I'd like to thank Jiacheng Zhang for his work on the experimental entrainment function calculations. And finally, the Department of Energy, thank you to them for funding this work. And thank you to the Caltech Department of Aerospace and the Division of Engineering and Applied Sciences for this wonderful opportunity and for hosting this talk.
Thank you very much, Bhavini, for a